All right, let's try this next one. And I just want you guys to keep in mind, on the exam, it's not going to be, stated what kind of problem it is. So we always want to be looking for, what unit is given here and what unit is asked for. So starting with moles and trying to obtain moles is just going to be a single molar ratio problem, whereas the previous was grams to grams, and that's clearly stoichiometry with 3 steps. Okay, so let's try to answer this one. Okay, obviously start the same way we start all these problems. Step 1, balance the reaction. Right, so clearly, like all the problems, we're going to start balancing the reaction. Here there's clearly an inequity for the oxygen. Okay, we clearly have to bring both of these up to some common denominator here. Okay, between 3 on the left and 2 on the right, so looks like 6 might work, which will require 2 out in front over here on the left. Okay, and a 3 out in front over here on the right. Then I'll have to bring the KCl up to 2 each. All right, so we need to be, pretty adept at doing that right from the get-go. And now we can solve the rest of this problem, trying to determine how many moles of the reactant, or of potassium chloride's form, if 9 moles of the reactant decomposes here. So again, reactant, those things on the left. Okay, and I'm trying to convert this into moles of KCl. I only need 1 unit factor to do so. All right, that exactly relates the moles of the reactant to the moles of product. We just call that a molar ratio here, taken right from the coefficients, which is just a 2-to-2 ratio here, so actually nothing happens, and we should get 9 moles at the end. So the correct answer should have been, J9 D'Amico. Should have been 9, which I believe was option 2. So I'll give you 5 bonus points for that. Remember, bonus points don't count towards your grade. Disclaimer. All right, onward. Same reaction, and now let's try a slightly different problem. Here we're told we are starting with 25.0 grams. I'm just going to write that down as given information here of my reactant. And I need some amount of grams of potassium chloride. Okay, this is grams to grams. So I've trained you well. You remember that there's going to be 3 unit factors here in this stoichiometry. All right, step 1, I already skipped, which I should have gone back and done, which is balancing the reaction, but we did that in this previous problem, so I'm just going to skip that step and give you the coefficients there for free. You already worked it out in the previous problem. And now we're ready to go. We have starting grams of this reactant. And like all these, again, we're going to follow the same roadmap here: molar mass, molar ratio, molar mass. Okay, so we need the molar mass of KClO3. We can consult the periodic table. We should get I suppose I actually need to calculate this. So oxygen would be 48 from that, 35.45 from the chlorine, and 39.1 from the potassium. So I get a molar mass of 122.55 grams. That'll take care of my unit of grams KClO3. Now I'm in moles of that unit, and I need to convert to the potassium chloride moles using my molar ratio. Again, it's a 2-to-2 ratio, so essentially 1-to-1. But that does take care of my units, and now I'm in moles of KCl. And I can get that into grams of KCl by using the molar mass of KCl here. Which I should get at 74.55. And I obtained 15.2 grams of KCl. Right, it's always going to have the same cadence to it: molar mass, molar ratio, molar mass, as far as the 3 unit factors here. Right, but it's still super important, especially before the exam next week, that we do enough of these that we can do them efficiently. Right, you always have to calculate molar masses here, so you should be good at calculating these numbers quickly as well, consulting the periodic table. Right, you should be quick at balancing the reaction here. Alright. And you should be quick at, actually doing the computation once you set it up. Alright, onward. Remember, you can always type any questions you want to see worked out or topics discussed in the chat. Otherwise, I'm just going to keep plowing through these practice problems more or less as a video walkthrough. Alright, so let's work through this next one. Given 24 grams of sodium chloride, react with some excess amount of magnesium oxide. How many grams of sodium oxide are made? Okay, so just taking these words and sort of relating it And boiling it down to our mathematical equation, I know I can first identify ultimately we're after grams of sodium oxide. Okay. Of course, I need to know the formula for sodium oxide. I know I'm starting with, or I'm given here, 24 grams of sodium chloride. And so this looks like a grams to grams type of conversion, so I know I'm going to need these 3 stoichiometric steps. And I'll need the molar mass for this given reactant. I'll need the molar mass for the desired product, and I'll need the molar ratio from the balanced chemical reaction. Okay, so I know I have to set up and balance this chemical reaction. I'm told here that it's sodium chloride reacting with an excess amount of magnesium oxide. Okay, so I need to know the formulas for each of these. Sodium, we've memorized the symbol for that, Na. Chloride, we know that suffix IDE denotes, it's an anion of chlorine, which we know is Cl. And then we sort of think about the ionic charges that these would like to obtain, and use that to sort of figure out the subscripts. And sodium would like to be +1, chlorine would like to be -1, so they're going to be in a 1-to-1 ratio to make my NaCl. Okay, magnesium oxide, we approach the same way. We know magnesium is Mg. We know that IDE, symbolizes the suffix for an anion. Here it's oxygen, so that's O. And then consulting the periodic table, magnesium is one of those alkali earth elements. Those all want to really adopt the +2 charge. Oxygen likes to be -2. It's a 1-to-1 ratio here, so that's also going to be just subscripts of 1 and be MgO. Okay, so we know those are the reactants. Those are the 2 things coming together. And then we're told there's some amount of grams of sodium oxide that are made. Sorry, you just missed out on the poll and the bonus points there. Sorry, I closed it a little too early. No worries. I'll leave it, I close it because it sort of takes up some space. But yeah, I'll leave it open longer next time. Sodium oxide is one of the products, so I need to come up with the formula for that. I know it's going to be some combination of Na for sodium and O for oxygen, but here I need to consult the periodic table or just recall that sodium wants to be +1 and oxygen wants to be -2, and so those are going to have to cross over and give us a formula for sodium oxide of Na2O. Okay, so that's one of the products here. Okay, the other product is kind of implied here, that this is a double replacement reaction, right? So these cations here, Mg and Na, trade in dance partners here, so Mg is going to wind up with Cl, and that has to be MgCl2 in order to get those ionic charges to balance. Right, so there's my formulas for other reactants and products. Now I can go through and balance these things, and we should be able to more or less do that in one go here by just putting a 2 out front of NaCl. Now there's 2 sodiums and 2 chlorines on each side, 1 magnesium and 1 oxygen on each side. Okay, so now I can approach the stoichiometry problem. 24 grams of sodium chloride, right? That's NaCl. I need the molar mass then of that NaCl. Which is 35.45 plus 23, 58.45 or 44. If you use the 22.99 for sodium. All right, so now I'm working in moles of NaCl. And I know this next step is going to be a molar ratio that relates that given NaCl to moles of the desired product. Sodium oxide, Na2O. Okay, consulting the coefficients in the balance reaction, NaCl, there's 2 of those for every 1 mole of Na2O. And then lastly, I need this molar mass here of Na2O. And that should be 61.98. Right now it's a matter of punching all these numbers into the calculator. And I obtained something like 12.7 grams, which I'm going to round to 13. So hopefully that's clear. Hopefully these are making sense, and you know, as long as you can set these things up, you know, you should be proficient by now at actually button mashing and coming up with the right number of sig figs in your final answer. And we also talked a lot about limiting reactant problems, which more or less are combinations of these stoichiometry problems. Okay. If you want to do more like this, I can do that. If you want to move on to limiting reactant, I can do that. You just have to let me know what types of practice problems you want to do, and I can do more of those. Alright, so this one's a little bit more aggressive. This is the limiting reactant ones we've been talking about. So hopefully this helps J9, D'Amico. Or is that supposed to be Janine? Probably not. So here's a limiting reactant one. I know it's a limiting reactant, so let's first quickly talk about how would I, identify this as a limiting reactant problem. Okay, how do I know it's not just a regular stoichiometry problem? Okay. I can still identify this as asking for grams of iron. Okay, so I know I'm going to be solving for that grams of Fe. But I can identify it by a limiting reactant problem because I'm given 2 different masses, okay, of 2 different substances. So I'm going to have to do 2 stoichiometry problems. Right, so I'm going to have to do one of these using the 200 grams of Fe2O3. And I know that I'm going to have to do another one for 300 grams of carbon. All right, I'm giving each one of these reactants here some amount, and asked for a single amount of product. All right, so I'm trying to figure out which one of these reactants is limiting this reaction. All right, and here I'm given the reaction already balanced. You can, and you should, go through and make sure things are balanced. But yeah, there's 4 irons on each side, 6 oxygens on each side, and 3 carbons on each side. So we're good there. Now I need to go through and just set up the 2 stoichiometry problems. And they're no different to set up than what we've been practicing thus far today. Okay, so I'll just set up all the units first, more or less our roadmap of what we're trying to do, going from grams of iron oxide to moles of iron oxide, then converting that moles to moles of iron, then taking that moles of iron and turning it into the desired unit of grams of iron. And now it's about filling in the appropriate molar masses. For iron 2 oxide, I get a molar mass of 159.7. Right, and it takes a little bit of time to calculate the molar masses, so don't think I'm just like coming up with them from nowhere. I'm calculating them as I go. And iron, I just happen to know, is 55.85 grams. I've studied a lot of iron chemistry, so that one is sort of ingrained forever in my brain. Okay, so from that 200 grams of iron oxide, I could make a possible 139.8 grams of iron, if there was enough carbon to completely react with that iron oxide. Alright, so let's go through and do the same sort of stoichiometry, starting with the other reactant. We'll just set up all the units I'm going to need. Still this familiar molar mass, molar ratio, molar mass. And this last molar mass in limiting reactant is going to be the same. I'm going to the same unit over here on the right because I need to compare those two to one another. Make sure I'm comparing the same unit, apples to apples here, right? Or irons to irons, as it were. So this last unit factor is always going to be the same in these limiting reactant problems. Then it's a matter of just setting up the necessary molar ratio and the 12.01 grams per mole of carbon. And calculating out the 1,860 grams of iron. Okay, but I'm not done. I still have to answer the question of how many grams of iron can be produced. Alright, so what do we think? could add these numbers, I could subtract them, I could pick one of them. What do I do with these two numbers over here on the right? I assume 4 sig figs even though there is no 0 after the decimal point on the given grams. 3 sig figs. So that decimal point, right, this decimal point right here, does signify that the zeros before it are significant, okay? So usually these trailing zeros don't count, okay? But if there's a decimal point here, like there is, then it matters, okay? Then those zeros count. So there's 3 sig figs here, actually. So, right, this 139.8, I should really round to 140 decimal point. Okay. Yeah, you're right. So, to answer the question, how many grams of iron are produced, I pick the lesser of these two numbers, 1860 or 140. I'm going to pick 140. All right, rounding it to 3 sig figs. And that trailing zero here in 140 is significant if I add a decimal point after it. Okay, so 140 grams of iron would be my answer. I don't add these two numbers together. Right, I just look at them, compare them, and pick the least one. 140 grams of iron. Okay, which means my iron 3 oxide here is the limiting reagent. And carbon is an excess. You're welcome. Right, so if you can master the limiting reactant problems like this, you've mastered basic stoichiometry because you're doing 2 stoichiometry problems in one. Okay. Here we didn't have to balance the reaction, but you know, in some of these, if you practice enough limiting reactant ones, you'll have to set up and balance the reaction too. So if you master that as part of limiting reactants, you've mastered balancing reactions as well. So it really is important to practice the limiting reactant problems, and tough ones, because if you can start to get those down, you've mastered a lot of what will be on the next exam for chapters 7, 8, and 9. All right, let's try one more, and then maybe we'll try a demonstration if I have any materials left over from this morning. I have to check. All right, so here we have phosphorus trihydride reacting with oxygen gas to produce diphosphorus pentoxide and water. And then we're asked how much of the diphosphorus pentoxide will be produced if I have these two amounts of reactants. Okay, so you should be able to identify the type or problem, and you should know what the first step is. It's always to set up and balance the reaction. So I'll give you a few minutes to set up and balance the reaction and start to work through limiting reactant. Alright, so hopefully we've gotten something like this as far as the various compounds. Phosphorus trihydride, tri prefix is 3, so we know that's pH 3. Combining with oxygen gas, so O2, that's one of the diatomics. It produces diphosphorus pentoxide, so P2O5. Right, diphosphorus is 2 phosphoruses. Pent, like pentagon, is 5-sided. Pent is 5, so 5 oxygens. That's P2O5 plus water. And then we can go through and balance. And I like to start with the largest sort of discrepancy here, or oxygen. Although that's by itself, so I suppose I should wait on that. Thinking about the most complicated, I guess, is phosphorus, since it's combined with hydrogen on the left and oxygen on the right. Let's start and try to balance that. So to bring up phosphorus on the left, I'll need a 2 out in front of pH3. And so now I have 2 phosphorus on the left, 6 hydrogen on the left, 2 oxygen on the left. Okay, so phosphorus is now balanced. My hydrogen is imbalanced. I can modify that with a 3 in front of water. Of course, that creates an imbalance in oxygen. And I need a 4 at the end, or a 4 in front of oxygen to bring that up to 8. Okay, so this one slightly more challenging than ones we've usually done, but this should be pretty straightforward, and you should be comfortable with this at this point. If you're not, sometimes starting with the wrong species makes it more difficult. You just get more experience the more you do to know which element to start balancing first. Oxygen's by itself, so I'm going to leave that to the end because I'll easily be able to balance that at the very end and not affect anything else because that just appears by itself. Alright, so step 1 is complete. And now we can proceed to the actual stoichiometry. We're given 17.0 grams of phosphorus trihydride. We know the second stoichiometry is going to be 16.0 grams of oxygen gas. What do we ask for? How much diphosphorus pentoxide will be produced? So I know in each case I'm trying to get to grams of diphosphorus pentoxide, P2O5. Okay, and now the roadmap's clearly laid out here. I know what I'm starting with and what I'm going to, and it's now a matter of filling in the molar masses and molar ratios. So go ahead and set that up and do that at this time. All right, so there they are set up with all the molecular masses. Remember, this last unit factor in each is going to be the same since we're going to the same product. This middle one is the molar ratio, and the first one is the molar mass of whatever I'm starting with. Okay, so take a couple more minutes to compute and select the final answer. Were you able to calculate either one of those or both? Yeah, I get 17.7 for oxygen 1. And for the other one? I get something like 35.5. Yeah, 35.5. So then I compare these two, and limiting reactant is going to be oxygen here. Oh, that was poor. Nice. Good work. So I think you're getting these. Right, that's all there is to it. That's basically as complicated as it's going to get, right? Setting up the reaction, balancing it, and then going through and comparing the two separate stoichiometry problems. Okay, so that's all I had prepared. So I think we'll stop there unless you guys have any other questions. And I can do another problem if you suggest one or have one in mind. So these are what are called, or at least what I call ghost bubbles. Basically a flask of just water and some dry ice. But the dry ice when you put it in the water, just start bubbling quite vigorously. I have this little soapy solution here, so I can basically trap that vapor, that carbon dioxide, basically the same stuff we breathe out, inside this bubble. Right, and then pop it. So here's a look at the actual flask. You can see just a small piece of dry ice down in there that is bubbling away, subliming. Right, that solid turning directly into gas. I just have this hooked up here that is capturing the vapor. I submerge under that soapy water solution, basically starts bubbling out. So this is a really good demo I do on Halloween for trick-or-treaters and things like that. They can hold them in their hand and sort of smash them and things like that. So it's pretty neat. Something really easy. Anybody can do a science demo, and it looks really cool. My dry ice is just buy it at Publix or any grocery. Just carbon dioxide that's really, really cold, solid, and it doesn't pass through the liquid phase. It doesn't melt. It goes directly to the gas phase. Okay, so we call that sublimation, and that's why we call it dry ice, because it doesn't melt and get everything wet like regular ice, but it's cold enough to keep your coolers really, really cold. Even make really huge setups and contraptions, so you can make the bubbles like really, really big. Alright, so tomorrow in class we'll do some demos, like a liquid nitrogen pumpkin and things of that nature. But we'll also learn a lot about gases in general as we start chapter 10. So I think I'll more or less stop there for today, unless you guys have any more questions.